What I want you to do now, for just 1 minute, I'll give you exactly 1 minute to do this. And this is, I'm going to give you this picture, and I want you to discuss with your friends. We've got now this object going up and coming down. I want you, that is now our reference point. Remember, up is positive and down is negative. I want you now to figure out for that little interval there, what is the sign of the displacement? Is it positive or is it negative for there? What is the sign of the velocity and what is the sign of the acceleration while going up? And then for that little interval there, again, what is the sign of the displacement? What is the sign of the velocity? And what is the sign of the acceleration? And then for this interval, I want you to figure out what is the sign of the displacement, the sign of the velocity, and the sign of the acceleration. So I give you exactly 1 minute, and then we'll have a look at what you've got to say about that. Right. Right. I hope you've got the answers now. Now, again, remember what I said right at the beginning. Above, on the positive side of the reference point, the displacement will be positive no matter what it's doing. So the displacement is going to be positive there, and there it will also be positive because that is above the reference point. The moment you are on the negative side of the reference point, this displacement is going to be negative. Right. About the velocity, while the object is busy moving in the positive direction, the velocity is going to be positive. While it's busy moving in the negative direction from there right down to there, the velocity is going to be negative, and the velocity is going to be negative. Right. And then the last one about the acceleration. What about the acceleration? Well, we've sorted that out right at the start, and that is that throughout the motion, acceleration will be negative, 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 because it's downwards throughout the motion. I honestly hope all of you had this 100% right. What I would like you to do is, when you get the opportunity, I want you to draw exactly this picture. But now I want you to take down as positive and up as negative, and figure out in the same way what the signs would be. Compare that with what your friends have got, and then if you don't agree, discuss it with your teacher and see if you can come up. And remember that if you get stuck, there's Moodle. You can always ask me about that. About the gravitational acceleration, the 9.8 meters per second squared. I think one should be careful not to use 10 meters per second squared, because on the data sheet it says 9.8, and we are supposed to use the values that are provided on the data sheet. I know it's going to make calculations a little bit easier if you can work with 10 instead of 9.8, but I think use what is on the data sheet, rather not 10. You know, if you have to do just a rough calculation or whatever, I guess it's okay just for yourself to use it as approximately 10. But when you do an exam, you use the values that are on the data sheet. Right. We are going to do apply this knowledge on an example right now. We are now going to look at the question that has been asked in the national exam November 2011. We are going to look at that problem now, and we are going to start with the question. It is in the first paper, question number 3. I hope you've got the question, but if you haven't got it, no problem, because I've got it here, and this is all about a camera. Right, it says here, a hot air balloon, that is the hot air balloon, is moving vertically upwards at a constant speed. All right, there it says VI, which is the constant speed upwards. A camera is accidentally dropped from the balloon at a height of 92.4 meters, as shown in the diagram below. The camera strikes the ground after 6 seconds. Now, this is not on the picture. I'm going to take away the question now, but we are going to keep the picture here. So it is after 6 seconds that it strikes the ground. And there it says, ignore the effects of friction. Oh, thank heavens. We don't have to worry about air resistance. We are just going to do a straightforward calculation with projectiles. All right, so that is the question. You've got it now, or not the question. That is the information that we've got. Now, the first question that we have to deal with is, they say, at the instant the camera is dropped, at that instant there, it moves upwards. Give a reason for this observation. Wow, why would that happen, that it moves upwards the moment, because it's dropped? Now, I think, again, let's go back to our bus stop. Now, you are now a passenger in the bus, and you see that very special person standing there at the bus stop, and you want to impress that person. And while the bus is moving, you jump from the bus, planning to do a very graceful landing, but you don't. You stumble. Now, why would that be? Why did that happen? What you must remember is, if you are in the moving bus, you are part of that system. You've got the same velocity as the moving bus. In other words, if the bus was traveling at 5 meters per second, you will be traveling at 5 meters per second. And when you jump from the bus, you will still be traveling in the same direction as the bus at exactly the same speed as before. And according to Newton's first law, you will continue with that velocity until some other unbalanced force changes that velocity. So if there's no air resistance, you will keep on moving in that direction at that speed until you hit the ground, and the friction of the ground sort of brings you to rest. But then your body still continues moving in that direction, and that's why the landing was not so graceful. So in other words, when you remove something from a moving vehicle, it will still have that velocity that it had inside the vehicle. Now, what you must remember, that in the case of the camera, this guy had the camera in his hands, and he was going up with a balloon. Whatever the velocity of the balloon, he was going up with a balloon, and the camera was moving along. It was part of the system that moved upwards. So the camera had a certain velocity inside the guy's hands. Now, the moment it was released, that camera, there was no funny force acting on it, so that camera would then still have that velocity. But now, it's got a velocity of, let's say, 14 meters per second upwards. Therefore, it will continue moving upwards because it's got a velocity. It's like a projectile with an initial velocity of 14 meters per second, which will then move upwards. So then it's only the weight that will slow it down, and that's why it will eventually stop and fall back. So that is now the first question that has been asked, and we've given now our reason for this observation. The second question says, calculate the speed VI at which the balloon is rising when the camera is dropped. So I have to calculate the velocity of the balloon when the camera is dropped. Okay, that sounds funny because I don't know anything about the balloon. I know about the camera. I know that it takes 6 seconds to strike the ground, and I know it's on a height of 92.4 meters above the ground. So I know a lot about the camera, but I don't know a thing about the balloon, just that it's moving upwards at a constant velocity. So how can I tell what is the velocity of the balloon? Remember that the camera will have exactly the same velocity, initial velocity, as what it had in the balloon or when it was part of the balloon system. And therefore, the initial velocity of the camera is exactly the same as the velocity of the balloon. So what they're actually asking me to calculate is what is the initial velocity of the camera. And then I can say, all right, so the balloon will be exactly the same. So I'm going to put my focus now on the camera and not on the balloon anymore. What is the initial velocity of the camera? Now, if we now think about what are the quantities that we've got available, we've got time, we've got the 92.4 meters, and we are dealing with a velocity here that we have to calculate. Now, at first glance, it sounds very much like the equation V equals delta y over delta t. That I can maybe use that because I've got a delta y, 92.4 meters, and I've got a delta t, 6 seconds. Why can I not use the equation that says V equals delta y over delta t? The problem is, if I use that equation gives me the average velocity. And if you've got a constant acceleration, like in this instance, it will give me the velocity somewhere in the middle of its movement at 3 seconds more or less. It will give me the velocity there. And this is not what we are about to calculate. I don't want to know what is the velocity somewhere there in the middle. I want to know what was the velocity at the start. And that equation is not going to give me that. That equation is going to give me the velocity somewhere else that I'm not interested in at this stage. I want to know what was the velocity at the beginning and not somewhere in the middle of that interval. So that equation is out. I don't want average velocity. I want initial velocity. But if I'm talking about initial velocity, that sounds like equations of motion. But I cannot use equations of motion whenever I feel like it. I must first check whether I can use it in this case. Now, what are the requirements for the equations of motion? Well, first of all, I must have motion in a straight line only. And by the way, that's why you are not allowed to use equations of motion for a pendulum, for instance, because that is definitely not a straight. You will get the right answer, but you will get 0 marks if you use it there. It's not a straight line motion, so you're not allowed to use equations there. But in this case, I've got a straight line. It's going up and down along exactly the same straight line. It's a straight line motion, and furthermore, the second requirement is it must be constant acceleration. Right at the start, you remember we said that while it's going up at the highest point while coming down, the acceleration is constantly 9.8 meters per second squared down. So I don't have a problem with any one of those two. I've got a straight line, I've got constant acceleration, so yes, I may use equations of motion. So now I can look at those quantities that I've got for equations of motion. Now, the quantities that we deal with when we look at equations of motion, the 4 quantities that we will find in those equations will be initial velocity, VI, final velocity, VF, acceleration, A, time, delta T, and displacement, delta Y. I'm just about to do a calculation with vector quantities. What is the first thing to do when you deal with vector quantities? Choose a direction as positive. They don't tell us, they don't give us a hint in this case as to as to what direction is positive. So we can decide it starts moving upwards, so we are going to take up as positive. And once again, you are 100% free to choose down as positive if you want to be alternative. There's no problem with that at all. It's absolutely up to you. They don't tell us in this question what direction. They don't even tell us by implication what direction is positive. So we choose. And I prefer to choose up as positive because this balloon starts going upwards. So up is positive, down is negative. All right. So that's now the first thing. And we are working with displacement, so we are going to work with a reference point. We will need that. And once again, it's always good practice to start with your starting point as the reference point. So there's our reference point. Maybe I should do it in red. That's our reference point, the starting point. Good. So I've done now what needs to be done before I can start with my problem. And now let's go through this list of quantities that I've got there to see which one of those applies in this case. All right, the initial velocity is what they asked me to calculate. So I put a question mark there so that I know the equation that I'm going to select must contain the initial velocity as well. Now, the final velocity will then be the velocity, if I now take the 6 seconds from there to there, it's going up and then coming down. The final velocity will be the velocity there. Do we know what the velocity is there? Well, I know that there are some people that say the velocity is 0 because it's when it strikes the ground, it just lies there. But please remember what we said, that we are dealing with projectile motion from the moment it leaves your hand until the instant just before it touches the ground. It doesn't touch the ground with 0 velocity. So we don't know what is the velocity there. It's not 0. And then it's not asked. So we are going to leave out that one. We are allowed to leave out one because all the equations of motion contain 4 quantities. We can leave out that one. Okay. And then we are going to look at the acceleration. Well, we know it's going to be minus 9.8 meters per second squared throughout the motion. And the time is 6 seconds. And delta y, that is now the tricky one. Delta y is the displacement. Oops, the only one that we've got is now the 92.4 meters. And what about that going up and that coming down? We haven't got that. Oh, but the problem is we are dealing with, or the solution is that we are dealing with vector quantities, displacement, which is the straight line from the start to the final point, from the reference point to the final point, which is just that. That is not part. Remember what we said, that displacement doesn't depend on the route that you followed between A and B. It is the straight line between A and B. So if that is where he started and that's where he ends, then that is the displacement, which will be, what will it be? 92.4 meters? Am I going to fill in there 92.4 meters? No. What did I say? All the displacements on the negative side of the reference point will be negative. So that is negative 92.4. This is very crucial that you know this, that you have to take into consideration that that displacement is below. If it had a displacement of plus 92.4, it would have been 92.4 above the reference point, but the fact that it is below on the negative side of the reference point, that makes it minus 92.4 meters. All right, so that is crucial. Now what we do now, we select an equation that contains these 4 quantities, and that is the equation that will contain it. And the only thing that you do now is you plug those values. Delta y goes in there. Vi is what I don't know. T is 6 seconds. It goes in there. And then A is minus 9.8. And then the time again, T squared is 6 squared. And you calculate the initial velocity is 14 meters per second. Right. What I would like to do now is to look at a graph of displacement versus time. Now, the most important thing that you must know whenever you deal with a graph of displacement versus time, you can't do graphs without this, is that the gradient of this graph, this you have to know, gives me velocity. Crucial. So in other words, whatever the velocity does, the gradient will do exactly the same. So if we've got now the object starts at, maybe we can just have this again there, okay? The object starts there, the camera starts there. Now, it starts at the reference point, so the displacement will be 0. It starts at the reference point. Now, it moves up with a positive velocity of plus 14. Now, what you must know about graphs is that a graph can have a positive gradient or it can have a negative gradient. And the gradient can increase or it can decrease. Some people battle to know when it increases. You know, when it becomes steeper, if you would, for instance, go on your bike and it becomes steeper and steeper and steeper, the gradient increases. If it goes flatter, the gradient decreases. This is a gradient of 0. So in other words, the steeper it is, the greater the gradient. The flatter it is, the smaller the gradient. Okay, now let's see. It starts with at the reference point, so it's got a 0 displacement. It starts with a positive velocity. And what happens to the velocity as it goes up? The velocity decreases. It's a positive velocity because it's busy going up, and the velocity decreases. So if we look at the graph, it starts with a positive gradient, right, which decreases. So in other words, it decreases until it's 0. At the highest point, it is 0. And then when it falls back, you remember what we said, that when it falls back, the velocity is positive. But what happens with anything that's falling? It falls faster and faster and faster and faster and faster until it hits the ground. So in other words, the gradient is now going to be negative because now it's got a negative velocity. The gradient is now negative and it's increasing. So in other words, it's going like that. So that is what your displacement versus time. The gradient tells you what the velocity is. Right, and then in the last place, I just quickly want to do a sketch graph of velocity versus time. All right, it starts, now once again, the one thing that you need to know about a velocity versus time graph is that the gradient gives you the acceleration. Very important. Now, it starts with a velocity, a positive velocity of 14. And then as it goes up, 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 the velocity decreases. At the highest point, the velocity is 0. So it starts there, plus 14. It's 0. And then when it falls back, the moment it reaches the same point as where it was projected, the velocity will then be minus 14. And then it will continue because it falls past that point, and it will continue and continue and continue for as long as till it hits the ground. So when it hits the ground, that will then be at 6 seconds. So this is then your velocity versus time graph, what it looks like. I would very much, if you now also look at the acceleration versus time, and the other thing about this graph is if you now take the gradient, you remember that we said the gradient is just the gravitational acceleration, which is minus 9.8 all the time. If you look at this graph, then you can see the gradient is negative all the time because the gravitational acceleration in this case is negative all the time. And if I would plot a graph of acceleration versus time, in this case, it will just be negative. It will be minus 9.8 all the time. Right. I want you to think about what all these graphs would look like if we have decided that we want to take down as positive. Now, I just want to summarize quickly what are the most important things that we've learned today. In the first place, whenever you do a calculation or graphs about vector quantities, step number 1 is determine what direction is positive and what direction is negative. Don't try to do anything without that. If you work with displacement, also determine what is my reference point. You can't work without that. And then the other thing is that with displacement, you will always find that as long as something is on the positive side of the reference point, the displacement is positive. If it's on the negative side, displacement is negative. While something is busy moving in the positive direction, the velocity will be positive. While it's busy moving in the negative direction, velocity is negative. Gravitational acceleration is always down. Please remember that. Now, I honestly hope that you are going to program that into this computer up there, that you got that, and that you are going to do lots of problems. And please, if you get stuck, let me know. Talk to me, please. I would love to communicate with you people. And then, until next time, good luck. God bless. Bye.